Testing 1, 2, 3. Hey everyone, welcome to Chemistry 1112. Dr. Carroll here. This is wu12 lecture 2. So, spontaneity, free energy lecture in your textbook. We are looking at page 573 and onwards. So, page 573 and onwards. And we saw that the second law of thermodynamics said that if a process is spontaneous, delta S of the universe is going to increase. But to get both the system and surrounding entropy changes is not an easy thing to do, not practical. Focusing on the system is an easier thing to do. The surroundings are often more complex than the system. So it'll be more convenient to determine if a system is spontaneous by just focusing on the system and not the surroundings. And to do that, we introduce a function that relates to both enthalpy and entropy. It is known as the free energy or Gibbs energy function. And we see here that it is H minus Ts. So it's a state function. G equals H minus TH. H being the enthalpy, T being the temperature in units of Kelvin, and S being the entropy. Now, you got to be careful because usually our delta H values are listed in kilojoules per mole and our S naught values are in joules per mole per Kelvin in tables like Appendix D. So we got to convert everything to joules and then at the end go to kilojoules, or else convert everything to kilojoules and take it from there. But you got to be careful when you do this stuff. It turns out that when I do the math, I simply get delta G equals delta H minus T delta S. That is the key expression. This is one of the top 5 equations in the universe, in my humble opinion, because it says, does something happen or not? It'll turn out that if delta G is negative, delta G of the system, which we end up just calling delta G, is negative, then it'll happen. We don't say how long it's going to take for it to happen, but it will happen. So that is a spontaneous process. If delta G of the system is positive, well, then the system is going to be non-spontaneous. Okay, so let's look at that for a second and look at the possibilities. And the book does this a little later on, but I like doing it now. So we've got delta H and delta S. And there's 4 possibilities: positive, positive, negative, negative, positive, negative, and negative, positive. Okay? So we want to get the value for delta G. If delta H is positive and delta S is positive, so it's endothermic, absorbing energy, and further it is getting disordered, then this will be a spontaneous process only at high enough temperatures. So it's spontaneous only if the temperature is high. How high? Well, more than 0 degrees Celsius if you're talking about evaporation of water, right? Evaporation of water is spontaneous if you have liquid water. So if it's more than 0 degrees Celsius in the surroundings, then some of that energy will be transferred into the glass of water, and the driving force will be the disorder in the system. If it's less than 0 degrees Celsius, well, you're not going to get evaporation. You can get other things, but not that. If they're both negative, then you're only going to get a spontaneous process if temperature is large, temperature is small. Only at small temperatures, because if you go to high temperatures, then you're doing minus and minus, so your delta G is going to become positive. If delta H is positive and delta S is negative, well, then it's never going to be spontaneous. It's going to be non-spontaneous always, right? Because delta H is positive minus, temperature is always positive. Delta S is negative, so it's positive minus a minus, which means plus. So delta G of the system would be positive always, so that would be non-spontaneous. If delta H is negative, and delta S is positive, then you're going to get a minus whatever the temperature is. So that's going to be even more minus. So that would be spontaneous always, regardless of temperature. That is the dream, to get more disordered, delta S positive, and more energetically stable. And the analogy I like to do is someone's on a ski hill and they go down the hill. So they're getting more energetically stable because they're closer to the ground. But as they fall, they broke their arm there, the poles are going everywhere, and it's a big mess there. So the entropy of them has increased. They've gotten all disordered, and that happens naturally. Now you can try to fight that, but then you're going to be sweating and going from liquid to gas. Well, that would increase the entropy as well, wouldn't it? So that is a process that happens all the time. Okay. Do we have here more descriptions of things, and maybe a bit too much information, but here we got the delta G naught is delta H naught minus T delta S naught. So the standard free energy change is delta H naught minus T delta S naught. Another way to calculate delta G naught is if you know the standard molar free energies of formation. Now you're going to say, hey, that sounds a lot like the standard molar enthalpies of formation. And you are correct, it does. And the rules are quite similar between the delta G naught and the delta H naught. I mean, if you have from Appendix D or some other appendix or set a table, if Appendix D isn't in your book, I guess your appendix was removed. I need a canned laughter button to put in here every now and then. We would have the delta G naught of the reaction is the sum. This is the gas mole coefficients. No, not necessarily gas mole. It's any kind of coefficients. It doesn't just have to be gas. Any coefficient on the product side times the delta G naught of formation of that product. Sum them up with all the other products minus the corresponding reactant data, and that gives you delta G naught of reaction. And as you can imagine, delta G naught of something like oxygen gas, that's in its standard state of formation, is going to be 0, just like delta H naught of formation of oxygen gas. So that's its standard state is 0. S naught is not 0, right? S naught of O2 gas is greater than 0. I forget what it was, 291, I can't remember. But you can calculate the standard molar free energy of formation by just using this equation, but you can only do that at 298 degrees Kelvin. If it's a different temperature, you can't do that. So the sometimes called the Gibbs-Helmholtz equation is this one here, and this is more robust in that you can look at delta G naughts at other values as well. Okay, so let's see an example. This looks familiar, doesn't it? Find the standard free energy change for the acrylonitrile synthesis described in example 12.5. Well, there's two ways. The first uses standard free energies of formation. The second uses the value of delta H and delta S. And the values should be very close to each other. So rather than waiting around for me to look up those numbers, I'm just going to go to the value. So we have 2 moles of C3H3N liquid, 6 moles of water liquid, right? Got to be careful with the phases. Minus 2 times the delta G naught of formation of C3H6 plus 2 times the delta G naught of formation of NH3 gas plus 3 times the delta G naught of formation of O2 gas. Well, look at all those parentheses there. Well, I haven't seen that many brackets since the last NCAA March Madness tournament. Hi-oh. Okay, so when we substitute in the values, you get minus 1122 kilojoules. Okay, and you're going to say, oh, that means it's spontaneous. You are correct. If delta G naught is negative, then the reaction is spontaneous. Now, if you didn't have those delta G naught formation values, but you had previously got a delta H naught previously determined delta H naught and delta S naught, then you can get delta G naught. So delta H naught from the previous example we did in the first lecture in this chapter, minus 13.7 kilojoules, minus R, 298.15, and delta S naught was minus 659. But if you want in kilojoules, you have to divide by 1,000, right? 10 to minus 3 kilojoules in a joule, fine. And you get minus 1121. So it works either way. Now we see here in the second calculation, the entropy term is positive. So delta G naught is a little more than minus 1317. More meaning closer to 0, right? So it's less negative. We're forming liquid water. It makes the system more constrained. Nevertheless, the large negative enthalpy change means that the heat becomes dispersed in the surroundings, more important than the others. We say that it is an enthalpy-driven as opposed to an entropy-driven reaction. So under standard conditions, it is a highly spontaneous process. If you were curious, when would this system not become spontaneous anymore? I'll put this off to the side. That's when delta G naught of the reaction is 0. Then that's your tipping point, and so you would get the temperature would be delta H over delta S. So at what temperature would it no longer be spontaneous? We make an assumption that delta H and delta S, their differences, they don't change much with respect to temperature. So minus 1317 over minus 0.659, right? Because you have to have it in terms of kilojoules. So this is going to be a real high temperature to prevent this thing from happening. 1317 divided by 0.659 is like almost 2,000 Kelvin. So this guy's going. You are not going to easily prevent products from forming here. You got to really ramp up the temperature to a high degree. Okay, let's try practice exercise 12.6. Calculate delta G naught for the combustion of methane producing liquid water under standard conditions. Okay, this one I think I'm going to do on watch this. Oh, do I have a space here? Let's see. On the paint here. So here we go. You think I would have all these numbers I've done before, but that would not have been fun, would it? We want to have fun with this. So we're going to talk about combustion of methane. So this is practice exercise 12.6. Page 576. PEX for practice exercise 12.6. So we got methane gas, CH4 gas plus O2 gas goes to form CO2 gas plus H2O liquid. Sometimes the conditions are such that it is going to be H2O gas. So we're going to have delta H values, delta G values, and S naught values. Yes, we always laugh when we say that, don't we? Maybe I'm the only one who laughs at that. But anyway, so now I got to look at Appendix D. So I'm just getting my a bookmark here, and this is all. What's the question asked at 298? Calculate delta G naught for the combustion under standard conditions. Okay, so that means 1 bar, 298. Okay, so now I'm on page 1072, and I'm looking for the data for methane, CH4 gas, and delta H naught is minus 74.6. That's kilojoules per mole. And what else do I know about CH4? I have that the delta G naught is minus 50.5. And the S naught, which is in joules, for CH4 is 186.3. Okay, O2, delta H naught, delta G naught of formation are 0. S naught for oxygen. Gotta go to the next page here. Is 205.152. Feel like I'm doing my taxes. Okay, and then carbon dioxide, we're going to have CO2. Where is it? There it is. Delta H naught minus 393.5. Delta G naught minus 394.4. And the S naught for carbon dioxide is 213.8, always a positive value. And finally, H2O. And be careful here because on a test you could see partial charts. You probably won't get the entire Appendix D, but you'll get like subsets of it. And they'll try to trick you. They'll give you H2O both liquid and gas. So here we're talking about the liquid. So delta H naught is minus 285.83. Delta G naught for H2O liquid is minus 237.1. And S naught on page 1073, 69.95. Okay, so now I'm going to jump back to the question here, and let's do it. Let's get the delta H naught of formation, and the delta S naught. We don't call it formation, we just call it delta S naught. So delta H naught of formation. So is this balanced? Ooh, hold the phone. I better make sure that this is balanced. CH4 plus O2 goes to CO2 plus H2O. Carbons are good, hydrogens aren't. I got to put a 2 in front of there, so that's good. And then I got to put a 2 in front of the O2. So I got 1 carbon symbol on both sides, 2 times 2, 4 hydrogen symbols on both sides, 4, 2 and 2 is 4 oxygens on both sides. Yeah, if it's not balanced, you aren't going to get the right answer. So delta H naught of formation is going to be minus 393.5 plus 2 times minus 285.83 minus 74.6 plus 2 times 0. Okay, so we're going to get 393.5 negative plus 2 times 285.83 negative minus 74.6 negative. So minus and minus. So I get minus 890.56. Okay, and that's going to be units of kilojoules. Okay, and delta S naught is going to be CO2. So 213.8 plus 2 times 69.95 minus 186.3 plus 2 times 205.152. So we're going to get 213.8 plus 2 times 69.95 minus 186.3 plus 2 times 205.152 minus 242.904. Now that's a joule, so in kilojoules it would be minus 0.242904 kilojoules. Okay, so if I use this equation, delta G naught is delta H naught minus T delta S naught, I would get minus 890.56 minus 298 times minus 0.242904. I don't know why I used all those decimals, but whatever. So 890.56 negative plus 298 times 0.242904 is minus 818. Hooray, that's what the answer is at the back of the book. Minus 818 kilojoules. Okay, so that's one way to do it, using the Gibbs-Helmholtz equation. The other way is using the delta G naughts of formation, which we're given here nicely. So the delta G naught of formation for CO2 minus 394.4 plus 2 times minus 237.1 minus 50.5. And hopefully that'll get pretty close to the same answer as before. So 394.4 negative plus 2 times 237.1 negative equals that, plus 50.5 is minus 818 kilojoules. Hooray! So there's a example, and we look and we say, okay, this is a spontaneous process because delta G naught is negative. So methane does want to burn. Now some of you are going to say, well, you know, the delta S naught, it's pretty close to being positive. No, it still is a little negative. Yeah, it's a little negative because I got 3 moles of gas going to 2. So getting a little bit more ordered here. But the amount of energy released is the driving force why this is going to happen. So this is what happens in your furnace. You might wonder, when would this system not become spontaneous anymore? So I'm going to just sneak something in here. I'll change the color of it. So that tipping point again. So delta G equals delta H minus T delta S, right? So if delta G was 0, the temperature would be minus delta H naught over delta S naught. No careful. Let's do this. Delta H over delta S. Delta H naught over delta S naught would be, again, the delta H naught and delta S naught don't change much. Negative signs go away, so it'd be 890.56. Let me just round it off to 891 over 0.24. 891 divided by 0.24 is 3,713 Kelvin. So we aren't going to get temperatures like that, okay? So we don't have to worry about this reaction suddenly becoming non-spontaneous. Once that spark comes, that methane is going to burn spontaneously, okay? At all reasonable temperatures, okay? If you got some furnace cooking at 3,700 Kelvin, you got some issues, okay? I would call Winnipeg Supply right away if that happens. Okay, let's use my Alt tab and get back to here. So we were talking about free energy and temperature. Let's scroll down a bit. And this is what I was just talking about. So delta G is approximately, at any temperature, delta G naught of the reaction can be estimated as delta H naught of the reaction minus T delta S naught of the reaction, where the delta H naught of the reaction is determined at 298, and delta S naught of 298. Now, if you take some more physical chemistry, you're going to have to make some corrections to this, but in the intro course, this is how we look at it, just like anything, right? You got to learn how to ride the bike with training wheels before you take the training wheels off. Okay. Now, immediate consequence of this equation is that spontaneity of any reaction, if you have a large delta S naught, then temperature is going to be more effective. If it's a small delta S naught, temperature is not going to be quite as important. But it's still good to be able to calculate it and to do what I did, that tipping point, to see when you go from spontaneity to non-spontaneous system. So let's look at this example here. Example 12.7, and we have here the dissociation of dinitrogen tetroxide into nitrogen dioxide. Show the reaction is not spontaneous under standard conditions. So I could take 2 times delta G naught, a formation of NO2, minus delta G naught, a formation of N2O4. And we want to see, is my delta G going to be less than 0? This is standard conditions. So delta G naught, the reaction is less than 0. As temperature changes, delta G naught must become 0 before it becomes negative. So in part B, we're going to find the temperature where it does become spontaneous. So I guess is that it is non-spontaneous at first. Let's see. So I get 2 times 51.3 minus 1 times 99.8. That's what Appendix D tells us. Let me flip to Appendix D and see if that. Just want to double check those numbers. Oh, I lost my bookmark. Okay, that happens. Oh no, I got it again. Nitrogen dioxide and dinitrogen tetraoxide. So I'm going to have NO2 gas. So it's going to be 51.3, good, minus 99.8, which is N2O4. Yeah, okay, that fits. And you end up with just a little non-spontaneous. Okay, so I mean, if you just look at entropy, it's saying, hey, we're going from 1 mole of gas to 2 mole of gas. But there's also enthalpy that's important. And all that's bundled in for delta G naught. And so this is pretty close. But it is slightly non-spontaneous. If you crank it up just a little bit, I think, then it'll become spontaneous. Okay, it would be spontaneous in the opposite direction. 2NO2 goes to N2O4. Okay, so when does it become spontaneous? If each pressure is 1 bar, so I'm going to delta. Okay, I got to calculate T is delta H naught over delta S naught. Delta H naught at 298 is 55.3. Delta S naught is 175.8. Divide by that 1,000. And so you see it's 315 Kelvin, which isn't that much higher than room temperature of 298, is it? So we have relative comparable amounts of NO2s and N2O4. And to make the N2O4 dissociate, become a spontaneous process, you just have to crank up the temperature a little bit. Otherwise, the NO2 combined to form N2O4 is a spontaneous process. And I know some of you are thinking a bit about a chapter we're doing fairly soon after this one, equilibrium, and you will have significant amounts, relatively speaking, of both the NO2 and the N2O4. So to summarize, at 315 Kelvin, delta G naught is 0. So all temperatures greater than 315, delta G naught is negative, and the decomposition is spontaneous. Does the results make sense? Decomposition requires a bond to break. That's why decomposition has a positive delta H, right? Same time the number of molecules doubles, which is right, delta S naught has a positive value. Positive enthalpy change means energy is removed from the surroundings and constrained, whereas the positive entropy change means matter is dispersed. Below 315, the enthalpy dominates, and the decomposition isn't spontaneous by that temperature. Above 315, the entropy term dominates, and decomposition is spontaneous. So that's good. You should read that over again if you want. Estimate delta G naught for the combustion reaction of methane at 1920. We just looked at the methane. Oh, but H2O is a gas here. Oh, really? Okay. Well, let's try it. Why not? You could see that I was really enthusiastic about doing that one, wasn't I? So delta G naught is delta H naught minus T delta S naught. Well, no, I can't even do that. I have to get delta H naught. I can do this. I can go to here, back to this one here, and let's do. Let's get the value for for H2O liquid, for H2O gas. I'm going to sneak it over here. Okay, I'm going to need the delta H naught and the S naught. I don't care about the delta G naught because you can't use the delta G naught of formation reaction if you're at a temperature other than 298 Kelvin. So H2O liquid, we already wrote those ones down. 35, yeah. H2O gas is going to be minus 241.83 for delta H naught of formation. Delta G naught of formation I don't care about. The S naught for H2O gas is 188.835. 188.835. So my delta H naught of formation is going to be, I'm just going to substitute in, instead of minus 285.83, it's minus 241.83. So without trying to write everything again, I'm going to take 393.5 negative plus 2 times 241.83 negative plus 74.6, right, minus a minus, and I got minus 802.56. And the delta S naught, instead of 69.95, I'm going to have 188.83. So you see there's a lot more entropy, 835, with water gas than with liquid water. So that makes sense. 213.8 plus 2 times 188.835 minus 186.3 plus 2 times 205.152, and I get minus 5.134. Now that's in joules, so divide by 1,000, minus 0.00 005134 kilojoules. Okay. Is that in joules? Yeah. Okay, so then delta H over delta S is going to be 802.56 divided by that value, which is a ludicrously high number. So I think I have made a mistake here. Estimate delta G naught for the combustion reaction of methane at 1920. Oh, no, I just haven't answered the question yet. So delta H is 802.56 negative. Delta G minus T, so it's 1920 plus 273 times 0.005134 negative. Yeah, minus 791. I was doing this tipping point question, but that's not what the question asked for. It asked that's what the value of delta G naught at that temperature, minus 1920 degrees Celsius. So it's minus 791 kilojoules. Okay, so this methane is still a spontaneous combustion process, even at a high temperature like 1920. Now, if you go a heck of a lot higher, well, then it can change. Okay, so let's see a little bit more here. We talked about entropy and changes in concentration. Well, what about free energies and concentration? Here there's a big buildup here, really big buildup. Let me get to what I want to get here to. Here we go. Okay. If you have changes in concentration, I know it took 2 pages, and you can go through the proof if you want, but equation 1213, which you would be given on a test, is if you have the free energy in a non-standard set of conditions, so not at 1 molar and or not at 1 bar, then you can get delta G by getting delta G naught of the reaction plus RT, there's our R, pops in again, 8.314 times the natural log of Q. What the heck is Q? That's a funny looking Q anyways. I wouldn't draw Q like that. Q stands for the reaction quotient, and that is the initial values. Oh, and now my pen has, oh, this happened before. Let me go to, yeah, the initial values, okay. So I'm going to have to use the paint to go through here. Let me, maybe I go back to draw, change my, no, it's stuck there, okay. Let's see, how much more do we have here? So Q is the initial values. So I think I'm going to leave it there, and we'll, I mean, that was a sort of a subsection, a good place to stop. So we'll start in the middle of page 580. We'll start at the beginning of page 580 in our next lecture. Sounds good. Have fun.